Let's talk about question 4.10 or 4.10. Okay, so what they give you is an equation, and they say use the symbol m for mass in the control volume and show that the continuity equation can be written in another form. So I'm just going to write it out here. So they want us to recreate this form from the continuity equation. So the first thing I'm going to do is rearrange it a bit so it looks a bit closer to the continuity equation. So I'm going to put the double integral first over the control surface and then put dm dt equals to 0. And now let's start from the continuity equation. We have the double integral, the control surface, of rho v n dA plus d dt, triple integral over the control volume of rho dv equal to 0. Okay, so the first thing you'll notice is we will need to work in separate terms. So I'm going to write down term 1 and term 2. Let's begin with term 1. So term 1 can also be written as rho v n, and what I'm going to do is put the area in here and move the differential operator to the outside. Remember, you can manipulate the differential operator. So the point behind doing this is we want to get to m dot. So if you don't know, m represents, or if you just want to know, m represents mass, okay? M represents mass. By putting a dot on top, you are implying per unit time. So anything with a dot on top is actually per unit time. So this is actually mass per unit time, or mass flow rate, or kilogram per second. So what you'll notice if we do dimensional analysis on this, density has units of kilogram per cubic meter. All right, velocity has units of meter per second. Normal vector does not have any dimension, and area has units of square meters. If you multiply this out, you get kilogram per second. So by doing this, we've essentially made it the double integral over the controlled surface of d m dot, because m dot stands for kilogram per second. So the first term is done. Let's do the second term. Now the second term looks slightly trickier because we have d dt, triple integral over the control volume, rho dv. All right, again we are going to manipulate the differential multiplier. Remember, as you move the differential multiplier, you simply just need to change what the integral stands for. So over here, I'm going to make it d dt over the control volume of d rho v. And I just move the differential outside. Now, once again, we're going to use the same method as before and do dimensional analysis. So density is kilogram per cubic meter, and that v is not velocity, as I wrote here. It's actually volume, so cubic meter. So you'll find that if you take cubic meter multiplied by kilogram per cubic meter, they cancel out and you're left with kilogram. So what this means is they specifically told us in the question, let m stand for mass inside of the control volume. So we can replace rho v with a capital M. Then you are integrating a derivative. So you're integrating dm. So outside of this whole thing will just become m. Because remember, you are integrating dm. Integrate a derivative, you get m out. Okay, I hope that makes sense. Of course, this won't be a triple integral anymore, but I'm just doing it to show you. Okay, this will become one integral because you're dealing with respect to mass in the control volume. All right, so that can be replaced with dm dt, just like that. So now, if you had to write out the full thing, it becomes the double integral over the control surface, dm dot plus d dt of m equal to 0. And that's exactly what we had up here.